A very good evening to all of you. We warmly welcome you all to the most awaited moment, which is the inaugural event of Isotalks, organized by the Society of Chemical and Process Engineering Students, University of Perera. I'm Pyumina Disha from the E18 batch of Chemical and Process Engineering, University of Perera. We are thrilled and pleased to bring forth the new undergraduates of the Department of Chemical and Process Engineering take pride in exploring the horizon of chemical engineering to thrive in academic and industrial careers. This program consists of three keys to mitigate the gap between their current academic curriculum and the sustainable world of industry and higher education. Isotalks consist of a talk series, which is a series of webinars with the industry and academic professionals. This is accompanied by a discussion series, which is a series of casual talks on the most interesting chemical engineering aspects. In addition to this, it consists of a workshop series that is programmed to brush up skills in working with simulation software. And today, we are making the launch of the first element of Isotalks, the talk series, Isotalks. So today we are going to commence the very first chapter of the talk series, Isotalks number 1, to address the theme, the role of chemical engineers in combating the climate crisis. And it's a great pleasure for me to introduce our speaker today for Isotalks number 1, Dr. Tharindu Dasun Perera. He is a postdoc at the Urban Science Group, Lawrence Berkeley National Lab. His current work is related to modeling and optimization of urban energy systems in order to improve the sustainability and climate resilience of cities. Prior to joining Lawrence Berkeley National Lab, Dr. Dasun was a member of Urban System Simulation Group at Solar Energy Building Physics and Lab at Swiss Federal Institute of Technology, Lausanne, and a member of the Thermofluid and Energy Research Group at the Department of Mechanical Engineering. United his PhD in 2019 at the Swiss Federal Institute of Technology, Lausanne. He is the recipient of several awards, including the Presidential Award for Scientific Publications, Outstanding Paper in Applied Energy Conference 2017, and etc. Dr. Tharindu has authored and co-authored several research publications which were presented at well-reputed journals such as Nature Energy, Applied Energy, in addition to international and national conferences. So, this is our guest speaker for the very first session in Isotalks organized by SCAPES. Personally, I'm excited to be here, excited about all the amazing and interesting conversations that we are going to have today. And without any further ado, let's warmly welcome our speaker for today, Dr. Tharindu Dasun Perera. Sir, the stage is yours.
Thanks, Pyumi. Hello, everyone. Good afternoon. So I'll share my screen with you. I hope all of you can see my screen and hear me well. So again, thanks Piyumi for the kind introduction. So as Piyumi introduced, so I'm Dasun Perera and I'm working at the Lawrence Berkeley National Lab. So to give you a brief overview of the work that we do and who we are. So we are located in California, San Francisco, but not today since I am on vacation these days in Sri Lanka. So we are a department of energy lab, so focusing more or less on the energy aspect. We are located close to the San Francisco Bay Area, California, right in the middle of University of California, Berkeley campus. So although we have been funded by the Department of Energy, we have been managed by the University of California, Berkeley. So there's a lot of members who are having affiliation at both the University of California, Berkeley, as well as Lawrence Berkeley National Lab. So before joining LBNL, I was a postdoc, as mentioned, at ETH EMPA in the Swiss Federal Institute of Technology in Zurich, the German-speaking part of Switzerland. And I completed my PhD in the École Polytechnique Fédérée de Lausanne in the French-speaking part of Switzerland. So welcome everyone. So today's speech is about the role of chemical engineers in combating the climate crisis. So in today's speech, I'll be discussing about three main parts, or my speech has been divided into three main parts. In the first section, I'll be discussing about the climate crisis, why we need to take it seriously. And then I'll be moving towards to explain or take you through a walk of some of our works, focusing on the energy system domains. What are the insights that can be brought from the research work that we have done so far, which will enlighten some insights towards the work that you are doing in chemical engineering, especially focusing on the fighting against climate crisis. So we are amid of crisis. So especially when you're coming to Sri Lanka, so you can find a lot of crises. You can find a lot of long queues for goods. So you find a lot of challenges brought by the COVID. So this is a kind of like a nice representation of what we are going through right now. So as you see, we are going through the COVID crisis as well as the recession. So both these kind of challenges have been faced, not just only us. So I've seen recently some paper articles on the economic crisis of Pakistan, the challenges in Lira in Turkey, economic crisis, and recently the high inflation in US is also kind of like broadly taken into discussion whenever we meet people. So the COVID crisis and recession is something that we kind of like encounter in day-to-day life. But something that we do not discuss a lot is the challenge brought by climate change. So I'll first try to focus a little bit about the challenges brought by climate change. So main challenge brought by climate change is the Dominos Effect. So incidents created by climate change can easily penetrate and generate a sequence of catastrophic events. So this makes us to consider, are we at a tipping point, or are we at a point of no return? When we consider some of the ecosystems, we have already witnessed that we are at point of no return, especially if we consider the melting of Arctic or Greenland ice layers. We see that it is very difficult to return back to the normal. So this is a nice figure that explains nicely about the Dominos Effect, the impact created by the melt of Greenland ice sheet on the entire world, which is published in Nature in 2016. So as you see, it is having a wide range of impacts, including the increase of salinity, increase of sea levels, increasing the dryness of Amazons, leading towards wildfires, and then triggering out El Nino. So such sequence of events, or such sequence of disastrous event triggered by climate change leads towards many adverse social impacts. This include increase of mortalities, as it has been reported recently in the Lancet. These are data for the number of mortalities due to heat waves. So if you see US, it's somewhere around 10,000 to 100,000 deaths due to the heat waves just in 2020. Similar numbers in Russia, China, similar numbers in Sri Lanka, perhaps 100 to 1,000. But this is just only due to heat waves. If we consider the number of mortalities in Sri Lanka due to climate change, it's quite high because we need to count the floods, which is also been driven by extreme climate conditions as well as landslides. So it's very clear the impact of climate change on the health aspect. It's not just health, it's having a clear impact on the economy. So these are some of the data that I've extracted again from Nature Climate Change. So as you may know that in 2050, it is roughly estimated that there'll be 80 trillion loss in the global economy due to climate change. And the more impactful thing or the more sad thing is majority of this impact will come in the Asian and African region. So what you find in these two graphs is the overall impact on the economy in Asia and Africa. So roughly speaking, it has been estimated that the GDP growth will be retarded close to 10% to 5% in both African and Asia region, depending upon the climate scenarios we are in. So it's a significant drop in the economic development, which will have a notable impact on the social, health and educational sectors, and as well as food security. So which will create number of problems in these sectors. As a result, they predict that there will be social unrest due to the climate change. So you can easily understand that climate change is kind of like triggering out many, many challenges, and it is far beyond the recession and COVID. So we cannot just relax and wash our hand and wait. So we need to take actions in order to face this challenge. So when it comes to facing climate challenges brought by climate change, you need to find the main culprit. So unfortunately, the domain that I work, energy sector, is the main culprit for the climate crisis. So as you have seen, as you may see in this graph, which has been extracted from the IPCC report, the Intergovernmental Panel of Climate Change in 2014. So the direct contribution of CO2 emission from the energy sector accounts somewhere around like 25% of the CO2 emission. But if you consider the transportation sector, majority of the CO2 emission is related with energy. And it's the same when it comes to the industry. Of course, there's a minor fraction in the agricultural sector, but when you combine all together, the man-made CO2 emission, which lead towards climate change, is around 70%. So anthropogenic CO2 emissions, so energy sector is responsible for the 70% of the anthropogenic heat, CO2 emissions. It's a large fraction. So this demands for a major change in the energy sector in the climate, in addressing the climate crisis. So these are some of the, so this change cannot be done within 1 day, 1 year, 10 years, 20 years. So we are focusing about a timeline up to 2100, right? So depending upon the ppm of CO2, in this kind of into 2100, we derive certain transition pathways. So where we are right now, and if we take different pathways where we will end. RCP 2.6 is a very ambitious one, which will lead to very low CO2 emission levels by 2100, and RCP 8.5 is a baseline or business as usual scenario. So which will lead to very high level of emissions. If we just take this RCP 4.5 and 2.6, right, in considering that we will have less impact on the environment towards the end of the century, you can see the amount of renewable energy integration that you need to incorporate into the existing energy infrastructure in these graphs. So these graphs related with different ppm scenarios, focusing on the transition pathways that is being explained in this particular graph. So if we consider the most optimal scenario, most ambitious scenario, I would say 4.6. So considering where we were at 2010, so which is somewhere around like 17%, we need to reach somewhere around like 30% by 2030. And from 2030 to 2050, we need to move from here to somewhere around 60%, and then 2100, somewhere close to 100%. If we consider the increase of renewable energy fraction or the contribution, you find here it's 310 times, 310% increase. So it's like almost 3 times increase in the renewable energy technologies when we compare to where we were at 2010. So it's a huge increase of renewable energy technologies. If we consider what we are going to achieve 2030, which still seems to be quite ambitious, it's an increase of 145%. This is the most ambitious scenario. The least ambitious scenario, so still we see that there's close to 180% increase in the renewable energy integration level by 2050, and it's somewhere close to significant increase again by 2030. So anyway, we have to increase the renewable energy penetration level or renewable energy integration level, which will be a major challenge that we have to face. So this significant increase in renewable energy technologies, or the capacities of renewable energy technologies, will lead to a significant change in the system design we had. So at the early of this century, or kind of like right in the middle, so we were having fossil fuel based generators combined with each other. And then towards last part of last century, so we started to move towards renewable energy technologies combined with the fossil fuel based technologies. And then later we try to move further, combining energy storage in order to further increase the renewable energy penetration level. But now we have understood that we need to move beyond the energy sector, and we need to decarbonize the transportation and building sector. So we have to further extend the limit of energy system that in order to reduce the CO2 emissions. So it's a big challenge. So we are going through a major transition in the superstructure of the energy infrastructure, while incorporating renewable energy technologies, minimizing the CO2 emissions, not just in the electricity sector, but building and transportation sectors. So this does not come quite easily, right? So this comes through very intense, very effort, with a lot of effort in the research, as well as in practice. So I've taken I've done some Scopus keyword analysis to give you some understanding about the research work which drives this change in the superstructure. So as you may see, if you do a keyword search in Scopus, the number of publications within the energy domain, right? So it increased somewhere around 300,000 publications per year. If you put energy in the Scopus and do a keyword search, so 300K publications per year. And it started something like 18th century, so 1850. And if you specifically focus on the energy system, and I put, instead of energy, I put energy system to limit the number of publications. So you see still it is somewhere around 100,000 publications every year. So it's very intense research. So there's a very big research community, which is quite ambitious. I just want to compare this with another field to give you an understanding about this number. So I just compare it with the number of publications that appear in natural language processing in computer science, right? So you just see the number of publications, it's somewhere around 10K. And if you consider the area has been started to kind of like boom since like early 2000, or maybe like after 2010, especially with the intervention of deep learning or machine learning techniques. But if you move towards energy, it seems like 1960s. So you can clearly understand the depth, effort that has been put towards in order to get the change that we have already obtained. But still, there's a lot of things to be done. So this effort has drawn towards a set of, this effort has been focused on two different aspects. So one is the experiment, or rather implementation aspect, at the same time the theoretical modeling aspect. So if you consider theoretical modeling, it started with basic assessment of thermodynamic models, and then moved towards, it has moved towards the network models, especially from the electricity side, where we try to analyze the stability and distribution of electricity in order to maintain reliable supply. And then it has moved towards more into system models in order to increase the renewable energy fractions, and it has been kind of further improving. If we consider the recent literature, right, in this sector, what we could expect, or what we could see is that we could see that there is a reasonable progress that has been made in the energy system domain recently, but we are gradually reaching towards a plateau, right? So this is the number of papers again that I've obtained in Scopus. And if you focus a little bit more into this area, right, we could see if you focus a little bit more into this area and conduct keyword search with energy and dispatch, which is the control of energy systems, you could see there's a progressive growth, and then we are gradually reaching towards a plateau. Plateau means the system, the area is gradually getting matured, but it seems that we cannot progress further and further because the complexity of the problem becoming more and more, the existing modeling architectures cannot handle it. Which means that when you reach towards the system model that we discussed, of course, it helps to kind of like consider complex arrangement in renewable and storage. But if we try to move towards more complex arrangements, such as buildings and vehicles, there are many limitations. As a result, what will happen is the literature is gradually getting saturated, or the number of publications getting saturated. So this problem is not only limited to our area. So what we did was, when we saw this one, we saw how the other areas has been kind of like addressing this specific problem. So the same problem was faced by pharmaceutical industry, so which also kind of like intensively using computation models. So you can see that the pharmaceutical industry using computation models, especially in chemical computation models, so you can see a progressive growth, right? But around 2010, 2014, they also started to get coming up to maturity, right? Plateau in the curve. So what they did was they tried to move from the existing computational or numerical models based on the bottom-up approach. They moved towards more data-driven approach or more artificial intelligence-based approaches. So they say that deep learning helped to predict the pharmaceutical properties by broadly learned knowledge-based molecular representation. So they use artificial intelligence along with the computation models in the domain of pharmaceutical industry. And what really happened was there was a significant increase again in the publication of deep in the area. So this kind of trend that you find here is the part that directly responsible for the trend what you find here, which means that because of the support of deep learning, there was a significant increase in the publication, because artificial intelligence helped to address the complexity, which cannot be solely addressed by the computation model. So we try to learn something from this, and then we try to adapt it. But I mean, we understood it before this paper was published. So somewhere around like 2015, 2016 period. So what we did was we understood that these models were having a lot of limitations, especially considering buildings and vehicles. So we introduced artificial intelligence in order to design the energy systems. So let me give you a brief idea about what artificial intelligence-based models or data-driven models is. So the basic models that you learn during your undergraduate, or most probably during your master's, are based on the white box models, where you use detailed analytical models, first principle derivation. This can be either deterministic or stochastic equation that use detailed submodels and use the physiological knowledge. So this is based on a very comprehensive bottom-up approach, and you can explain everything on it. But the main problem is when you move towards a very complex system, it's very difficult or challenging to model such system entirely based on bottom-up approaches or white box models. So this is the main challenge that we face even in the energy system domains. So that is where we try to move from these bottom-up or analytical models towards something known as black box or data-driven models. So in which we try to use empirical models, which is a statistical based approach, or data-driven models, which is towards more complex, for more complex systems. So empirical models, or which we call as statistical models, have been used to understand very simple relationships that are been difficult to understand using the white box or analytical models. And the data-driven or the computational learning is being used to understand very complex relationships. So in between white and gray box models, you find gray box models, which use a little bit of data-driven, partially data-driven and partially physiological knowledge-based approach. So the present state of the art for the energy system was mainly driven on the white box approach, especially in the energy system design process. So we try to introduce the black box models. But jumping from white box to black box is not straightforward. So I'll skip this slide to save a little bit of time. So what we did was we introduced directly the gray box models. So which is in between white box and gray box models. So we introduced fuzzy logic in between to the design process of the energy systems. And then what we did, then what we observed was we were able to get a very high level of renewable energy penetration levels, as well as very high performance, very high performance, very upgraded performance levels for the systems. I'm not going to discuss these slides in detail. Of course, if you're interested, you could go through our publication in Applied Energy. And the next step was to move from gray box towards black box models, where we completely use artificial intelligence. We use a machine learning technique called reinforcement learning in order to understand the operation of the energy system. So we consider a complex energy system, including renewable energy technologies, conventional energy sources, storage, which is connected towards the heat as well as thermal energy network. And we were quite happy to see that there's significant performance in the improvement in the energy system optimization process, because the artificial intelligence can consider a very complex operation, which cannot be considered in the other instances. So there's significant improvement in the performance of the system. So what we try to do in simple is that we try to move beyond the system models existing architecture by introducing data-driven or artificial intelligence and come up with to address more complex energy system designs. So what is the outcome? So with the introduction of artificial intelligence, we were able to handle more complex problems that were difficult to address before using the existing models. So one such thing was something known as urban heat islanding issue. So urban heat islanding is something that you would find in cities. So you might find the temperature in the cities to be a little bit higher and the wind speed inside the city is a little bit lower. As a result, what will happen is, if you consider a building stock, the energy demand in buildings are for cooling is a little bit higher compared to the rural areas. So this is the plot for the cooling demand. So it's the negative heat demand. I'm sorry, in Europe, so you are typically plotting the heating demand. So what you find in the dark black line is, you find in the black line is, you consider the heating demand when you consider the urban heat islanding. And what you find in the gray line is the heat demand for the rural areas. So what you find here is that there's significant increase in the cooling demand. So this notably influenced the energy system. So in order to find how it influenced the energy system, so we need to come up with a flow of models, combining the updated energy system models that we have developed with the other set of models. So what you find in this yellow line is the energy system solution for the energy system, and what you find in the red and blue line is for the energy system that is for the rural area. So this is for the urban area and this is for the rural area. What you find in y-axis is the net present value or the cost, and what you find in the x-axis is the grid. So what we found was that when you consider the impact of urban climate, there is a significant increase in the cost, because there's an increased cooling demand, as well as there's a significant change in the demand profile. So this increase in cooling demand makes it really challenging to incorporate renewable energy technologies into the urban areas, at the same time go through the energy transition towards a more sustainable energy infrastructure in urban areas. So these conclusions drive quite wide interest. So our work was kind of like presented in our university main website, as well as highlighted as outstanding paper in the Applied Energy Journal. So this is one example of what you can do with the introduction of data-driven models towards the design. So one other thing that we could work is to understand the impact of climate change on the energy systems. So as I tried to explain you before, depending upon the CO2 concentration. So what really happened is there are different pathways that you can take. So RCP pathways. Depending upon the pathway that you take, the global mean annual temperature will be influenced, and the regional temperatures will also be influenced. So if I try to present it in a more sophisticated manner, so there are different RCP pathways. Depending upon these different RCP pathways, it will be having an impact on the climate, which will be presented by global climate models at global scale, as well as regional climate model at regional scale. So what we try to do is we try to incorporate all these different models and try to see what would be the impact on these kind of different scenarios on the energy systems. So considering such a wide, such a broad set of models and scenarios was helpful for us to understand the impact of future variations of climate and its impact on the energy system, especially during the extreme events. So we were able to understand what is the total impact of these uncertainties on the renewable energy generation, as well as energy demand, and then quantify this impact. So in this paper that we published in Nature Energy, we were able to show that there is a significant fluctuation in the grid interactions, the way that the system interact with the grid, and the cost when you consider the climate uncertainty or the fluctuations brought by climate change. So when you have a significant variation or significant change in the way that you interact with the grid, what would happen is there's a very high probability that there can be a significant drop in the power supply when you go through an extreme event. So which means like very hot or very cold climate conditions where the renewable generation is quite low. So which we call as compound impact. So for example, we were able to show that the energy infrastructure can go through blackout with drop in power supply probability somewhere around like 30% during such extreme event. So the results got quite wide media attention. So our results was directly showing the impact of climate change on the renewable energy integration process and what would be the energy resilience during such extreme events. So our work was published in 30 media outlets, so covering countries like Switzerland, Sweden, Spain, Australia, US, France. Unfortunately, I was not a single Sri Lankan one, but I mean, it was fine because I mean, we were not kind of like focusing on the Sri Lankan context in that time. But the most interesting thing was there was not much energy systems having higher renewable energy fractions as we discussed in this paper. But ironically, so this paper was published in 2020 January, and just after 1 year, for the first time, there was such an incident where you have higher renewable energy fraction in an area that came across with an extreme climate event. It was the Texas power failure that took place this year, February. So there was, so we were the first group of researchers who were able to predict that power failures such as Texas could take place and it could be very disastrous. The Texas power failure ended up in 200 casualties, and the economic impact was 200 billion US dollars. So you know how challenging it is during right now to find a 1 billion US dollars in the Sri Lankan context. So the total impact was 200 billion US dollars in Texas. So we were quite happy to see. Of course, we were not happy about Texas power failure, but we were quite happy to see that we were futuristic to kind of like forecast that such collapse or such challenges could be faced by the energy transition. So these are some of the work that we did. So I'm not going to discuss too much about the work that I was involved in, but just to give you a brief glimpse. So we're working on concepts such as urban cells, which I'll discuss briefly in this slide, but other concepts such as energy internet, integrating renewables to cities and things like that. Getting back to the main topic, so we've been discussing about the reducing the CO2 emissions in a broad scale. So as you may see in this one, so the energy sector has been responsible for a majority of the CO2 emission, but reduction of CO2 emission at the global scale, even in the energy sector, although it has been coming through energy sector or energy sector indirectly responsible for it, we have to work along with transportation and industry sector, where I think the chemical and process engineers play a major role, especially in the industrial sector, because they're having a much more broad understanding about it. So therefore, there's been a lot of discussion that has been taken place how chemical engineers can contribute towards improving the developing mitigation strategies for climate change. So one such thing is been kind of like presented in Frontiers blog, so it is from the Frontiers journals. So they say that they can, chemical engineers can work on renewable energy technologies, CO2 capture systems, as well as other technologies in order to improve, in order to minimize the impact. So these are 10 different areas that has been highlighted in ICHEM that chemical engineers can work in order to minimize the climate change. So it includes system thinking, working on renewables, sustainable bioenergy, sustainable foods, and things like that. I know there are a lot of ambitious undergraduates and maybe master students with us, so who might be quite interested on developing technologies to fight against the climate crisis. So there have been a lot of such technologies that has been developed. So you might be seeing that if you consider dye-synthesized solar cells, so which has been kind of like initiated by a concept by a professor at EPFL, my previous affiliation. So every time when you increase the efficiency by 1%, you either end up with nature, chemistry, or science, you see, right? So it's quite influential, the developing of, therefore you could understand that developing technologies is quite influential. So otherwise you cannot come up with papers in nature and science, right? But unfortunately, we find a totally drastic trend right now. So I'm not going to discourage anyone who is going to come up with a solar PV panel technology or a energy storage technology. But I would like to present what is happening right now globally. So this is some information that I've extracted from a Nature Energy paper that was published almost 2 weeks back by one of our colleagues in ETH SUSTEC. So what you find here is the global trend of patents, which means how frequent or how fast the technology is coming out, right? So, and these are not just simple patents. So these are patents maintained by the European Patent Office, and these are high impact patents. So high impact patents are patent families protected by at least 2 judiciaries, right? So 2 legal systems. So if you consider the CCMT inventions, which is the climate change mitigation technologies, you find a significant increase in the number of high impact patents, right? Up to 2013, right? And then what you find is that the rate is gradually getting slower, which means, of course, there are patents coming out, high impact, right? But the rate has been reduced. So if you compare these two, you would understand. So the reduction in rate, you could understand. So you compare the rate with 1995 to 2012, right? So you see there's a significant increase, right? So there's significant increase in the number of patents, 14% 5 increase, 16% 6 ICT into climate change mitigation, but then it has dropped towards -10 when you move into 2013 to 2017. So if you dig deep, right? Dig deep, right? Sorry. What you find is in these technologies, you see there's significant increase in patents for renewables, storage, and hydrogen, right? Up to 2013, right? And then the significant drop when it comes to renewables. The most drastic thing is the PV panels, right? The significant increase in organic PV, especially dye-synthesized and perovskites, and then it has also started to go down. So this is where the chemical industry lies, right? So there's not a significant increase either. So what we could understand is if you consider individual technologies, right? Of course, there is a growth. Fine, there's no problem. So if you plan to come up with a totally new PV technology, of course, go for it. But globally, what you can see is, of course, there is a trend, but it is no longer the trend that we observed almost 10 years back, right? So it has reduced a lot, and we are gradually getting maturity, technological maturity. So if I go back to the slide, right? So maybe the slide that I discuss here. The required renewable energy integration levels, right? So we see that all the technologies where we are right now, right? So we are slightly higher than 2010, right? So we cannot expect significant change, right? So such a significant change by just one technology or two, because we are because our technologies are gradually getting matured, right? Such significant change in this kind of, which will come up with like 300% increase to a 200% increase in renewable energy penetration level just by one technology, one disruptive technology will never happen. So that is where we need to think a little bit different. And that is where I think, I mean, we need to kind of like try to move towards something beside being limited towards the innovation sector in the technological. So there was quite an interesting article that was published in 2018 in Science, right? So which introduced this ecosystem concept where the energy system is going to be linked together or kind of like work in harmony with the chemical and process industry. So as you see that we have an energy ecosystem, which is slightly moving towards building sector and industry, but not much in harmony. But Davis et al., which was published in which they publish the paper in Science, they try to incorporate the chemical sector in a more comprehensive manner, coupling both energy and chemical and process sector together. So you find the renewable energy generation and renewable energy system or energy-based systems in this particular sector. At the same time, you find the renewable-based chemicals, renewable-based fuels in this sector, and both these sectors are working nicely in harmony. So this brought a new kind of like interest in the Europe, something called as sector coupling. So which means different sectors work in harmony while improving the sustainability of each sectors. So the chemicals chemical and process industry, I believe, is one nice example for sector coupling. And it has been kind of like widely discussed now in the European Union, in the IEA, as well as IRENA, which means the broad, all the main bodies that has been related with energy. And I know very well that it has been widely discussed in the Department of Energy in the US as well. So all the main bodies related towards the energy is focusing a lot on the sector coupling, which means how the chemical industry can be harmonized with the energy system and come up with a more diverse ecosystem of for urban areas. So this further extend the system models that we discussed before, moving from generation 3 to generation 3.1, 3.0 to 3.1. So where we could consider both energy ecosystem as well as the chemical and process industry together. And the next point that I believe would be quite interesting is that moving from the centralized architecture towards the decentralized architecture. If you consider the energy sector, it has already moved from the centralized architecture towards the decentralized architecture. And the next challenge is harmonizing the chemical and process industry with the energy sector to move from centralized architecture towards decentralized architecture. Centralized architecture has been the key because of the scale of economy. So, but the thing is, when you move from centralized architecture to decentralized architecture, you can incorporate more renewables. At the same time, you can reduce the cost of transportation. And in addition, what you can do is you can increase the flexibility at the periphery or at distributed level, so which you can increase the renewable energy penetration level. So there can be significant change in improving the sustainability levels. So the main challenge that you have is that you need to come across with when you move from centralized architecture towards a decentralized architecture from the energy system perspective is that how to come up with the efficiency as well as flexibility while maintaining the economic balance so that it will be not kind of a loss for the companies. So this has been widely discussed in our paper, which we introduced a novel concept called urban cell concept. So we did not discuss about the chemical and process industry, so we limited our focus towards the energy, building, and transportation sector. So we consider the sector coupling, interaction between the sectors in energy, buildings, and transportation. At the same time, we consider the interaction between different localities. So the main challenge that we have when you move from centralized architecture towards a decentralized architecture is that whenever you move from centralized architecture to decentralized architecture, you need to improve the interaction between these sectors and make sure that the supply chains works very efficiently in order to function this decentralized production in an efficient manner. So that we introduce as spatial coupling. So we consider the interaction between the different sectors, which we call as sector coupling, and then the interaction between different cells, so units, through the spatial coupling. So we consider the energy, building stocks, and electrified transportation. So we saw that we could improve the renewable energy penetration by 25% with the introduction of urban cell concept. And more importantly, the cost of infrastructure can be reduced by 37%. So significant cost reduction. One of the main challenges in transforming the existing energy infrastructure is the cost problem. So this could be addressed with the urban cell concept. So this extends the energy system models or superstructure of energy system models that we discussed before. So which move towards a new generation of models. So we were able to introduce a new generation of models based on system of system architecture. So we have different systems interacting with each other through multiple ways of interaction. So maybe transportation from ground. So it can be thermal networks, maybe gas networks, or maybe electricity networks that we have. So like the grid. So the system and system modeling framework gives us to get a holistic understanding what would happen when you move from centralized architecture towards decentralized architecture, not just considering energy, but considering energy, buildings, transportation, possibly in future chemical and process industry. The final part of my presentation moves slightly beyond urban cell concept to move beyond these physical interactions that I mentioned before towards cyber interactions. So as I mentioned before, decarbonization of transportation, materials or industrial sector depends, and building sector depends a lot on the interactions that you maintain between each other. So at one end, building sector, transportation sector, maybe industrial sector depends a lot on the energy sector when incorporating more green energy technologies. On the other hand, these energy technologies help to increase the flexibility of the grid, which help to increase the renewable energy penetration. So it's a win-win situation for both the sectors. So typically, energy markets work at 1 hour time resolution, and now it has moved towards a 15-minute resolution. If you are going to increase renewable energy levels up to a very high level, it need to the energy markets will move towards very fine temporal resolution, maybe like 1 minute or maybe in seconds. So such a highly fluctuating or such highly varying markets will require very prompt responses, where you cannot simply kind of like where you cannot simply limit your attention towards the physical interactions. In such instances, we need to move from physical interaction to the cyber interaction. So cyber interactions need to help to maintain this physical interaction in a more efficient manner so that you have more flexibility and accommodate more fluctuations brought by renewable energy technologies. So this is a very broad concept. So the physical networks that we discussed before, the connections between different industrial sectors, different buildings, followed by the energy infrastructure, needs the support from different sectors known as application, several set of virtual layers, by sensing such as sensor networks, communicating, powered by 4G technologies, and application layer like decentralized artificial intelligence. So these virtual layers will drive the cyber interactions while you have the physical interactions in a much more efficient manner. So which means that you need to move beyond the industry 4.0, which is industrial Internet of Things, and you need to connect the, you need to transform the, you need to digitalize the chemical and process industry while improving the flexibility in order to and incorporate it, with the smart grid, smart buildings, as well as electrical transportation, so that you have an efficient interactions, which will be another challenge towards all of you. So this brings to the final part of my presentation, last few slides. So this further extends the complexity of the energy infrastructure, energy superstructure, moving from system of system models towards network of network models, more complex interactions, which is enabled by cyber interactions. So I'm quite happy that we were able to work, we were able to help toward the evolution of energy system models from generation 3. And I hope that this modeling effort that we have done to move from this level towards the network of network models will have a critical impact towards the improving of the renewable energy penetration level. Before conclude, what I would say is that there will be a significant change in the energy infrastructure, which has been facilitated by the other sectors such as chemical and process industry, buildings, transportation. And as you saw before, most of the goals are set for 2030 and 2050, which means that you will be working as active members in the engineering community, which means that you need to take the responsibility and you need to be a part of this change. So I believe that all of you will, I'm looking forward to see the contribution of you in maybe journals, publication, in conferences, in making this change to happen and making a mark in the present in the energy domain. So to wrap up the things, we come up more and more frequently extreme climate events, which demands for a quick actions. Making energy infrastructure green is vital to address the climate crisis. And as I mentioned before, the artificial intelligence help to come up with the main bottlenecks in transforming the existing energy infrastructure to be more green. And you cannot do it alone, so you need to be coupled with the other sectors, and chemical and process industry engineering plays a vital role in this regard. So of course you can develop technologies, I never say no, so it plays a very important role, but at the same time the system thinking, system-based approach can play a significant role since we are reaching the technological maturity right now. So spatial coupling, sector coupling will play a major role, where we need to move from the centralized architecture towards a decentralized architecture, and maintaining flexibility, agility while moving towards a more modularized architecture will be a major challenge for the chemical engineers, which I think that you all will be able to solve. And this brings towards the end of my presentation, and thanks a lot.
Thank you very much, sir, for the valuable and insightful address to our topic today, the role of chemical engineers in combating the climate crisis. That was tremendously informative and thought-provoking for all of us. I'm pretty sure our audience are ready to move on to another appealing and intriguing segment, which is the Q&A session. Dear audience, we are ready to give you the opportunity to raise your questions. You can use the icon on the control panel to raise your hand to indicate, and simply type your question in the chat box. So this opportunity is yours to get your doubts clarified and enrich your knowledge. And we already got some questions during this speech. So I will refer to the first question. Sir, how far this climate crisis solved using modern technology, and can we reduce it to very low level?
I think it's a very broad question actually. It's very difficult to give a very specific answer for this question, because I mean addressing climate crisis is not just kind of like only limited towards developing technologies. It depends a lot on the implementation and policy level. So so I could take a simple example. So you can have a very advanced technology, but if no one is using that technology, then there's always a problem. So it's very difficult to give an exact solution on this one. So how far it can be solved, because it's not just only developing technologies, it's kind of like implementing it. So that is the main kind of like focus in the COP27, which was recently finished in Glasgow, UK. So to kind of like enforce the policymakers, the politicians, to use these technologies in order to address the climate change. But still, it's not kind of like very easy. So there's a lot of bargaining because it does not come very easily. So what I could conclude is that it is how we could solve the climate crisis. Of course, the technological development helped, but it's not just a problem with technological enhancement. So there's a lot of things. So there's a lot of economics, a lot of policy aspect, a lot of system level thinking, as we discussed before. Yes, thanks. Thanks a lot for the question.
Thank you, sir. Very clarified answer. And Rashmi Mohatti, the chance is yours.
Yeah, thank you, Kini. I have a question, sir. Like, now you showed a lot of statistics on the number of researchers that have been published currently. but the crisis is still here. So is there any limitation? Are there any limitations or challenges when it comes to transforming this research into practice? Like where does this stop us?
Yeah, it's again a good question. So the question, if I understood it correctly, so you have raised the question. There's a lot of research, but still the climate crisis is there. Of course, what I feel is that of course there's a lot of research which has come across with a significant change as well. So if you see the renewable energy integration level, so maybe I'll share it with you again. So this research has helped to come up with okay, maybe I need to go a little bit up here. Yes. So yes, sorry. Okay, I again went back. Sorry. Yeah, so there's been a lot of research that has been taken place. So this research has addressed major challenges in energy domain, right? So first thing that you could find is that you can find a battery in your phone, right? So you can still find energy that you can use the phone for like 2 days. So the energy crisis is, I mean, the development in the energy has been kind of like broadly influenced a lot of things, right? So first thing is you have a reliable power supply right now. And for Sri Lanka, it's like almost 98. So this comes with a lot of investment, but at the same time, a lot of research. If you consider Africa, so there's a lot of interesting things happening with the penetration levels of the grid. So you can find a small phone where you can have a battery for like 2 days, and then you have electrical vehicles that has been running. So there's been a lot of improvement in energy sector that has been happened. But the level of change that we have, or the challenge that we have, is far more beyond what we could achieve so far from the technology. So there's still a reasonable gap, right? So a part of these gaps can be kind of like filled with the invention, as I mentioned before. But then the rest, of course, you need a lot of things. So beyond the individual component level towards the research on system levels, how these different components can be brought together, and how this knowledge can be more broadly disseminated towards the other countries, and how the policymakers or people who are working in the policy side could be kind of like pushed to kind of like follow these things and to encourage the engineers. So it's a big process. So if you ask me, I mean, another question, are you satisfied about the researchers? So can we address entire problem with the technologies right now? So it is again quite an interesting question. So if you consider this IPCC, so the scientists are confident that the technologies that we have right now and the evolution of technologies that we go through can handle the climate crisis. But still, we need immediate action, and taking the action is beyond the level of scientists or understanding the impact of climate change and coming up with mitigation technology. So you need to deploy them. So I think the main challenge that we have right now is kind of encouraging policymakers to kind of like take this seriously and deploy these existing technologies. I hope that I give you a reasonable answer for the question.
Yes, sir. Thank you so much.
And also, Akila Lakshan is here with us. Akila, here is your chance.
Thank you, Pumi. Sir, my question is, other than the measures which have been taken to reduce the current crisis, what are the measures that have been taken to roll back the impacts which we are already facing?
Yeah, that is also interesting. So I mean, so if you consider the graph that I showed you, maybe I go back here. So here you see these. Maybe I'll make it large. Yeah, so here you see the CO2 emission, the evolution of CO2 emissions, right? So you see, I mean, you can find certain CO2 emissions right now, and then what we anticipate, right? So reducing it, of course, naturally there can be kind of like carbon CO2 absorbers. It's like the chorus and things like that. At the same time, you can do it artificially as well. So there is only about the CO2 emission, but it does not show what is the impact that has been already done by the changes that has been taken. So that is what I try to explain you at the beginning, right? I'm not a climate scientist, so I'm sorry if I make a mistake. But what I could say is that, of course, there are certain things which is been highlighted in the Nature paper, right? So we have already reached a point of no return, which means that we cannot kind of like bring back the system in certain areas to the normal condition. So it's not for everything. So bringing back CO2 towards normal level does not bring everything back, right? So because the impact on the ecosystem cannot be entirely bring back to the normal. So yeah, so but still there's a lot of technology such as it's been done to, one thing is to reduce the emission levels in existing technologies, at the same time to take out CO2 from the atmosphere, like direct air capture, like carbon capture and technologies.
Okay, sir. Thank you very much.
And also, sir, there is another question. Is carbon capture and utilizing technology a valuable solution for reducing rising level of temperature, thus fighting the climate crisis?
Yes, it is. I mean, it's an interesting area. So negative carbon technologies is it's a quite interesting area. Sometime back, I mean, I tried to work with Narish as well about the CO2 capture, direct CO2 capture. We tried to work with the company when I was at Zurich. So on direct air capture, which is a real nice job with direct air capture of CO2 emissions. So yes, it is. And the interesting thing is actually you can combine it with energy systems, because it depends a lot on the pressurizing as well as taking thermal energy. So which the process can be nicely integrated towards the urban energy system. So it's a promising area. At the same time, it can be something that easily incorporated into the energy system. So we can come up with a nice ecosystem. So that's why it's becoming more and more promising, and there's a lot of companies coming out now. Yes,
Thank
Nadish.
you.
Yeah,
Please, sir.
thank you, Dasun, like delivering a very insightful, comprehensive talk, like to give us kind of it was an eye opener, like what is happening around the world, like when it comes to the energy system modeling and where are we now in terms of global perspective. So I have two quick questions. The first one, like since you are like attached to one of the national level, US national level entity, so like you all are generating new knowledge to the scientific community, like how efficiently or how quickly these findings are absorbed by the US government, like how that link is being generated, and how practical, like when it comes to transform your findings into the real scenario. That is the first question. And my second question is for chemical, especially for chemical and process engineering graduates, like what are the opportunities available at your the institution, in addition to modeling, energy system modeling related stuff, like different, especially like related to renewable energy, developing novel renewable energy technologies, and like progression of other solar PV and other the technologies, like what opportunities are available from your end. Thank you.
Thanks, Nadish. Thanks for the commendation. Actually, thanks a lot for the invitation as well. So first, I'll talk about the knowledge transfer. So first thing is that, okay, the research model that you find in US is slightly different from the research model that you find in Switzerland. So typically in Switzerland, it's the government entirely funded research program that drives everything. But it comes to US, it's the Edison model, right? So that funds, which means that you have to do industry related research. So the one main advantage of LBNL being in the San Francisco is that you are right in the you're just a side of Silicon Valley. So there's huge amount of startups. There has been kind of like transforming the knowledge, not just only from LBNL, from UC Berkeley, from Stanford, from Caltech as well, and then coming up with this one. So the knowledge transfer has been at one end driven by the private sector, right? So we have colleagues that we work with Apple and then Google and Facebook, especially in they are developing a large, really big campuses. At the same time, they work along directly with the industry, not just not on the application side, but directly on the component level. And then the other one is the Department of Energy, so which is the main funding source for us and the state, California state. So for us, the Department of Energy has been kind of like focusing now, I mean, very strongly, especially with the new administration, President Biden, that there's a lot of things, a lot of the kind of like encouragement towards the fundamental research that help to kind of like enhance the research with the industry. So there's been government support towards kind of like fundamental research. At the same time, there's been direct interaction with the industry that we work on. So going towards the second question, the opportunities. So there are opportunities directly at the campus level from UC Berkeley. So UC Berkeley is very strong. At the same time, you have Stanford. So both of them are very strong when it comes to the renewable energy sectors. I think the Stanford is ranked it like maybe #1 in the energy sector now, energy domain right now. So there's a lot of opportunities. So there's opportunities at the system level. So what I discussed right now. At the same time, there's a lot of opportunities in the building sector that I work. So in both Stanford as well as UC Berkeley. So in UC Berkeley, we have the we have Center for Built Environment. At the same time, in the LBNL, you have the Building Technology Division. So where we take intern students from anywhere from the world. At the same time, UC Berkeley accept, as well as Stanford accept both master and PhD students. So in addition to them, so we have a National Renewable Energy Laboratory in Colorado, which also focus on renewable energy. They're working, they're doing a tremendous job, especially in the system level. And as you said before, PVs, perovskites, and all those PV technologies and storage as well, chemical storage, thermal storage. So they also take intern students. At the same time, you can apply towards positions in the University of Colorado Boulder, along with the NREL as well. So this is how these government institutes work with the private sector, from knowledge transfer as well as the opportunities that we have. I hope you, I gave
right,
you.
Right, thank you. Like in the future, like in case our prospective undergraduates, like they want to, pursue in that particular field, I think you will be, we will support us, like, directing the possible opportunities. And I think at some point you can share your email address with our student, and then, supporting our students, especially prospective students, to directing them, like, where the opportunities are abundant. Right. Thank you, Dasun. Thank you very much.
Thanks.
Thank you, Dr. Nagesh. And Dr. Manipura is also here with us today. Sir?
Thank you very much, Pemi. Thank you very much, Dasun. Congratulations, very hard work. And you're trying to figure out one of the most complex problems that probably the human face at the moment. And my question is a little bit the side that you are a little bit interested on, not a little bit, your focus is more on the system thinking and modeling, and how those soft side of tools can help to reduce the GHG emissions in future. My question is this: you're talking about the scale of economy, decentralized manufacturing systems. But if you look at your own picture, what you had in the background, there are a lot of concrete structures. At the same time, that is one of the basic needs of the human, like shelter. On the other hand, the second one is the food, where fertilizer is unavoidable. If you look at those two industries, actually those two industries are driven by the scale of economy. Otherwise, you can't give those products into the price that is competitive in the market. How practicable is...
Yes, there is a... Yeah, okay. Sorry, just go ahead with the question.
Sure, thanks. How practicable is to decentralize this kind of large industries? And is it a kind of a bottleneck for progressing the chemical industry towards GHG emission reduction? Thank you.
Thanks a lot, Aruna, for this question. Actually, there was, of course, we work with, of course, we are from the building technology division, so we work with chemical process engineers in our division as well as Berkeley. So the urban cell concept was something that we published in somewhere this June. So that was one major criticism that we came up with. Can all the chemical industries transform directly to something totally decentralized? Or how can we come up with there's another extension of this? Can you come up with such a efficient because such a decentralization need to have a very well connected supply chain? So is it possible? The answer is, I mean, it's difficult to say for me because I'm not an expert in chemical and process industry. But of course, there has been so when I was at ETH, so there has been already certain work that has been started to work on this aspect. So they have identified few industries, not the all, as you said before. So the chemical industry, so maybe if you consider like Haber process, I think there's kind of like many challenging things that you come up with because it depends a lot on the scale of economy. But on the other hand, there's been a lot of work now taking place to kind of like come up with modularized superstructure. So that is what I've tried to mention in the presentation as well. So it is important to come up with a modularized superstructure with the scale of economy, addressing the scale of economy. At the same time, you need to increase. So it's not just modularization is important, but you need to modularize it in a way that you have more flexibility. So having both these things are more challenging. But on the other hand, what we need to see is that when you go towards a decentralized superstructure, one of the main factors that drive the scale of economy is the cost of energy. So if you can come up with very low cost of energy, especially for most of these industries, because for example, cement, paper, the energy cost plays a major role. So if you can reduce the energy cost, right? So there's a separate kind of like economic setting that you come up with. So it's very difficult to say the present condition, what would be the kind of like direction, because it's kind of like an open question. But I could say is that there are both pros and cons, and there'll be a certain point that we can come up with more kind of like advantageous aspect or the more positive side of it. So the same question I would say that we came across in the electricity grid as well, because the centralized generation is way more economical than the decentralized energy. So still, it is very difficult. You know that the PV costs are very competitive with the coal, but the PV is not stable. So still, even in the decentralized, so when you have this storage and everything, when you try to stabilize it, decentralized is not kind of like fully economical, but we had to move towards it. So I will bring up a nice example for this one. So the economic concept has been brought even with the what do you call this? Let me take this slide. Actually, this is something that I presented to the Department of Energy sometime back. If I could find this slide. Yeah, so maybe I'll share this with you. Unfortunately, I don't have the exact thing. So this was you know, famous anti-slave act that came up in US, activated, right? So when we try to go towards the decentralized systems, right? So what people was complaining was, okay, I mean, the main challenge is the cost, right? And it's not reliable. And the same set of arguments, exactly in the way came up when you try to remove the slavery. So it was not economical. People say that the agriculture will collapse because you cannot run it, the agriculture without slaves. But with time, people move away from slavery and come up to a more liberalized society. So I think it will be the same when it comes to renewable energy, because we see how the change is happening and people have understood it. But moving towards a decentralized architecture, I think it's pretty ambitious and it's a very open question. But I still believe that the changes in economy brought by the decentralization of energy will drive it someday. I hope that I gave you an open answer for it.
Thank you very much, Dasun. It's, I mean, it's not trying to find really you have all the solutions for the problems. What I see is the way that you analyze the systems gives us a lot of insights, how the system level thinking would help us to predict various scenarios. Actually, that will help us to make new innovations to address the gap, which is very, very insightful. If I am allowed to ask Piyumi, can I ask another question? Because Dr. Dasun hinted something very interested to me. And if
Yes,
I am
sir.
allowed,
Sure,
I
sir.
can ask.
Okay,
All
sir.
right,
Sure,
thank
sir.
you. Dasun, you told that the kind of spin-off or the technology startups in the US, when you present this kind of information, because there is a large community who can see the opportunity. And the people like you move from Sri Lanka to Switzerland, then to US, and you are actually shining up with the new knowledge, and there is a market for it. My question is nothing to do with your technological understanding of these energy sectors or the emission reductions. What this particular thinking style in these countries, whereas Sri Lanka is lacking? Is it cultural? Is it about just like we want to survive with what we have? What is this? What is your experience? There's nothing technical. This is a social aspect that I would really like to hear from you.
That's a very tough question. Frankly speaking, I mean, the thing is, I mean, of course, there's a lot of people, a lot of colleagues that a lot of colleagues of mine work in the industry in Sri Lanka, so in the electricity sector, in the energy sector, and of course, my supervisors in Sri Lanka has been kind of like leading figures in the energy sector. So I don't want to kind of like make any complaints or say that okay, these sectors are not working well or things like that, because it's not. It's something that I think it's not something I could do. I would like to do, but what I could say is that of course when you're moving from Sri Lanka to Europe, so the entire culture is different, and from UK to US, it's completely different. So there are always pros and cons. So for example, if you consider the US, as I said before, so the innovation has been a lot of driven by kind of like more what do you call more radical kind of like thinking. So there's a lot of research outputs that we come across, but industrialization is very low. But if you move towards the US sector, so even in the government labs, as I work, so we work very close with Silicon Valley, and we work very close with the policy level. So the implementation has been taken quite seriously. So at one end, so you need to consider the radical movement or the progression in science, right? So at one end, you need to kind of like consider the dissemination, how it is going to be impactful to the industry. So I think in Sri Lanka, you need to consider both these aspects quite seriously. So the progression in science, which is very important, but there's always challenging that you cannot kind of like fund the progression of science unless there's a dissemination. So that's why in US, so you consider seriously about the dissemination. So at the policy level, at the same time, industry level. So I think the main problem that we have in Sri Lanka is that we do not have an ecosystem to sustain either the progression or the dissemination. So that is the main thing that I have seen. So one possible thing that we can do is that it's very difficult to kind of like come up with some change. For example, the energy models that we are working is some of the models that we started developed like in 1988. So for example, the Berkeley simulation models. And some of the models that I've worked with Switzerland has been kind of like bottom-up model from bottom-up model by our lab. So I never use a single library during my PhD or my postdoc. So all the things in computation models we develop on our own. So we did not depend on anyone, and especially in national labs, we seriously take it. So we do not take library from somewhere, implement it, we take some software, we don't do it. So we try our best to develop everything. So one other thing that we are missing is the continuation. So it's very important to kind of like reach, be radical, to move. So towards sustain something, you need funding. At the same time, the academicians should think of dissemination. So how the knowledge is being kind of like distributed broadly. At the same time, funding, academicians should take seriously about continuation of works, because unless you continue for a long time, it is very difficult to come up with these studies. For example, if you consider climate change, the models that we're working is like It's very complex, very difficult, and it is a huge ecosystem maintain this kind of models because it's not an individual effort. So the other aspect is the collaborativeness. So how far you are ready, you are open, and you are helpful. So because some of these climate models, they don't even get an authorship for the papers that we publish because we use data from 13 climate models in the paper in Nature. And we don't even appreciate them because it is climate data is open for everyone. So there's an ecosystem that is being need to support it. So there's a lot of elements that is been missing, but I never complain about the situation in Sri Lanka. I think Sri Lanka is doing really well. There's a lot of enthusiastic people. We have the passion, we have the energy. So I hope that it will be directed correctly in future, and we'll come up with impactful research in future in Sri Lanka.
Thank you very much, Dasun, for your insights. And I really appreciate sharing your many thoughts about various aspects with us today, with our students and my colleagues and all of us. Thank you very much and stay safe.
Thanks a lot.
Yeah, thank you, Dasun. I'm Anushka here, head of the department. So thank you very much for your for the knowledge sharing and yeah, making some insight. Thanks.
Thanks a lot. It's a pleasure.
Thank you, Dr. Manipura, and thank you, Dr. Anushka. And thank you very much, Dr. Dasun Perera, for your very valuable explanations. We believe our audience was able to look into a different perspective of the world with the knowledge you shared with us. And now I would like to invite Mr. Milindo Gamake, the event co-chair of Isotopes, organized by the Society of Chemical and Process Engineering students, to give the vote of thanks.
Thank you, Pumi. Good evening, ladies and gentlemen. Today, we witnessed the launching of Isotopes, organized by the Society of Chemical and Process Engineering, University of Perera. The main purpose of this initiative is to equip our undergraduates with auxiliary knowledge and skills to boost their confidence before they enter the world of industry and academia. On behalf of the Escapes, it's my privilege to deliver you the vote of thanks speech and acknowledge everyone, those who dedicated their time and energy to make this a reality. First and foremost, I would like to mention the guest speaker, Dr. Tharindu Dasun Perera, for not only sparing his invaluable time for us to grace this occasion, but also for enlightening us with his commendable talk on the subject. Thank you, sir, for your putting your best effort to make this a reality. And I would also like to thank our beloved staff members of the Department of Chemical and Process Engineering for their valuable contribution, guidance, and encouragement in all our efforts. I would also like to mention my sincere gratitude to the Senior Treasurer of SCAPES, Dr. Nadish Adasuriya, for coordinating the guest speaker. Furthermore, I would also like to thank all the members of the SCAPES and the students of Department of Chemical and Process Engineering. Last but not the least, I also thank the participants for their valuable time, because without your presence, we wouldn't have been able to make this event a success. Thank you again for your attention. Thank you.
And thus, we have come to the end of this amazing session. Hope you all had a wonderful time with us. Thank you everyone for joining us today amidst your busy schedules. So, with the hope of meeting again on another memorable day with an inspiring topic, it's time for us to wind up today's session. Good night, everyone. Stay safe.